Welcome. In this video, I will give an introduction to limits. Let's start off with the definition of a limit. And here, I'm talking about the limit of a sequence of real numbers. Okay, so following this definition here, suppose you have a sequence of real numbers. So that means you have infinitely many real numbers. We say it converges to the real number s, provided that for every epsilon greater than 0, there exists an index n in the natural numbers such that for all indices n, if little n is bigger than big N, then the distance between Sn and S is less than epsilon. So, a way to think about this visually is to imagine the number line, and your limit is S. The sequence Sn is converging to S if the terms of the sequence are getting arbitrarily close to S. That means we can go far enough out into our sequence in order to have the tail end of the sequence be as close to S as we want. So if you give me any margin of error for however small epsilon is, I can go far enough out in my sequence to guarantee that the remaining terms are within that interval. Okay? And another way to write this actually is to say, so Sn converges to S as n goes to infinity, if and only if, for every epsilon greater than 0, there exists an index n such that Sn plus 1, Sn plus 2, Sn plus 3, ... all the rest of the terms belong in the interval S minus epsilon to S plus epsilon. Okay, so think about it. If my point here is S, and I have a margin of error that's epsilon, I'm saying that the distance between my nth term and S is less than epsilon. That is equivalent to saying that my nth term is in this interval from S minus epsilon to S plus epsilon. Okay, so if Sn converges to S, this is the notation we'll use, right? Or just writing here, Sn goes to S. And that's what I kind of did right here, right? Sn goes to S. Okay, the number S is called the limit of the sequence, and a sequence that does not converge is said to diverge, okay, or be a divergent sequence. So a convergent sequence is a sequence that converges to a real number S. And I'm going to highlight that because we are not at this point including infinity as a possible limit, right? So if you converge, that means you're converging to a real number, okay? You're going to need to have this definition memorized and be very, very familiar with it. So let's go to some examples, and we'll practice using the definition to prove some of these limits exist, and also to prove that some of these sequences are divergent. So I'm looking here, and at the first one, you might remember from calculus that if you have a ratio of polynomials, one thing you can do to determine this limit now I'm looking here, is to simply divide by the highest power, right? So here I've got an n to the first power and an n to the second power in the numerator and the denominator. So I would just divide everything in the numerator by n and divide everything in the denominator by n. So then I would have like 3, and then that would be 1 over n, 7, and then 4 over n. And then you would say, okay, well, 1 over n is going to go to 0 as n goes to infinity, right? 4 over n is going to go to 0. So this numerator is going to go to like 3 plus 0. And the denominator is going to go to 7 minus 0. So this ratio is going to go to 3 over 7. The reason that it's okay to think like this is actually because of the limit laws. And in the next section or two, we'll prove the limit laws, okay? For now, let's use our intuition to figure out what the limit is. So we say, okay, from calculus, we know this limit is equal to 3 over 7. And then we can go back and use the definition to prove that the limit is what we say it is, right? So if we wanted to prove that this sequence, let me actually erase what I had here, prove that this sequence, the sequence whose terms are 3n plus 1 over 7n minus 4, that sequence converges to 3 over 7, we would use that definition. And let's actually sketch that. So let's see here. So the goal is going to be to prove that 3n plus 1 over 7n minus 4 converges to 3 over 7 as n goes to infinity. Okay. Now let's do the scratch work to actually prove this, because in order to prove this, this is my term Sn, and this is my limit S. And remember, I need to show that for every epsilon greater than 0, there exists an n such that n bigger than n, little n bigger than big N, implies the distance between Sn and S is less than epsilon. So I'm going to take this as my Sn and this as my S. Yeah? So if I do that, I want 3n plus 1 over 7n minus 4 minus 3 over 7. I want that to be less than epsilon. Okay? Now I'm playing around with this, and what must be true about little n in order to guarantee that this inequality holds? Well, I'm going to just work with the left-hand side and the right-hand side. So over here on the left-hand side, I'll actually get, so that'll be 21n plus 7 minus 21n minus 12. That over 7 times 7n minus 4. Okay? So I'm going to subtract in my numerator, and I'll have 7 minus negative 12. So I'll have 19 in my numerator. In the denominator, I'll have 7 times 7n minus 4. And I'll have the absolute value of that. So I'm wanting this to be less than epsilon. Okay? Again, I'm working on my scratch work. I've got to figure out what must be true about n in order to have this satisfied. I say, okay, well, that'll be true if and only if 19 over 7 times the absolute value of 7n minus 4 is less than epsilon, which is going to be true if and only if 7n minus 4 is bigger than 19 over 7 epsilon. Okay? I'm looking here at the right-hand side, and I notice that if little n is a positive integer, then this distance is just going to be equal to 7n minus 4. I really don't need the absolute values because the inside can't be negative because I'm assuming that my n is positive. It's a positive integer. Okay? So now I say, oh, okay. So now 7n minus 4 needs to be bigger than 19 over 7 epsilon. So then 7n needs to be bigger than 19 over 7 epsilon plus 4. Okay. So n needs to be bigger than 19 over 7 epsilon plus 4. And then all of this divided by 7. So my computations show me that if n is bigger than 19 over 7 epsilon plus 4 divided by 7, then the distance between 3n plus 1 over 7n minus 4 and 3 over 7 will be less than epsilon. So this is what I've found so far. I found that if n is bigger than this, then this is true. Go back to what I wanted to show. I wanted to show that for every epsilon, there is an index n after which this is less than epsilon. So it makes sense to let this be my n. Because if n is bigger than this, then the distance between my nth term and my limit is less than epsilon. Okay, so then there's just one last trick, which is, remember we have written here that we want n to be a natural number, big N to be a natural number. This may or may not be a natural number. There's a way to get around that. We can just use the ceiling function. Remember we talked about this in class. So I'm going to put it all together and say, this is for my formal proof. So let's say here, hypothesis is that Sn is equal to 3n plus 1 over 7n minus 4. And S is equal to 3 over 7. Claim Sn approaches S as n approaches infinity. Proof. Fix epsilon, or let epsilon greater than 0 be given. Choose n equal to the ceiling function for this, which is 19 over 7 epsilon plus 4. And then all of this is divided by 7. Okay. Then, for all little n bigger than n implies n is bigger than what I have in here. Okay. And that's going to imply 7n is bigger than 19 over 7 epsilon plus 4, which is going to imply 7n minus 4 is bigger than 19 over 7 epsilon, which is going to imply that the absolute value of 7n minus 4 is bigger than 19 over 7 epsilon. Which is going to imply, now let's go back and see, what did we do? I'm basically working my way back here. So we're at this step. We took the reciprocal. So then epsilon is bigger than, got it, okay. So this is going to imply that epsilon, right, so the epsilon goes here, bigger than 19 over 7 times that. That was 7n minus 4, which implies epsilon is bigger than, and then we had 19. Okay, this is what we had. Then we had absolute value of 19 over 7. And then that was equal to that, which was equal to that. Yeah. So that's our Sn. Minus 3 over 7. Let's say as desired. Okay. So that's it. Perhaps you can tell that proving that these limits are what we think they are can get very complicated very quickly. And that's all the more reason to prove the limit laws, and then we can just invoke the limit laws instead of having to go all the way back to the definition every time we want to prove something, right? But we're just in the beginning. This is an introduction to limits, and so I am taking the time to go through and show how to verify that the definition of a limit is satisfied. So let's look here. We want to say that the limit is n goes to infinity of 1 over n squared. Well, we know that's going to be 0, right? As n gets bigger and bigger, the reciprocal is going to go to 0. And for this one, this should be pretty quick. If we're looking at the limit as n goes to infinity, 1 over n squared, is that equal to 0? So we say let epsilon greater than 0 be given. Now what am I going to choose as my n? So say for all positive integers, little n bigger than n implies blah, 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 which implies blah, 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 which implies blah, 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 which implies that the distance between 1 over n squared and 0 is less than epsilon, as desired. So this is like the overall format, and we've just got to figure out what goes in here. Now, I want to say, this is what I want. This is where I want to end up. So I'm thinking, okay, if I have 1 over n squared is less than epsilon, That's if and only if just 1 over n squared is less than epsilon, because everything in here is non-negative. Okay? And again, I can just take reciprocals. Remember, you can't just take reciprocals if you're dealing with negative numbers, right? But none of my numbers is negative. In fact, I can just take the square root. So I say, let me let big N equal the ceiling function for 1 over the square root of epsilon. And then I'm done, okay? So you can go back and fill in the parts here. N squared is bigger than 1 over epsilon. Epsilon is bigger than 1 over n squared. And, maybe you could do a few more, but there you go. Yeah, that's good right there. You're done. Okay. For the third one here, limit n goes to infinity, -1 to the n. This sequence is just going to oscillate in between -1 and 1, -1 and 1, -1 and 1. And the terms are going to oscillate in between -1 and 1. So that means that the terms are not getting arbitrarily close to any real number. So this limit does not exist. And then lastly, when we go to compute the limit as n goes to infinity of cosine of n pi over 3, I think this one oscillates in between like -1/2 and 1 and 1/2 and -1, I think. So this one is also going to be does not exist. Let's prove that this limit doesn't exist, because it's important to be able to show that a limit doesn't exist using the definition as well. So we want to prove that this oscillating function does not converge. So let's see here. So hypothesis is going to be Sn is equal to -1 to the n. Claim is that Sn diverges. Okay, so for proof, let's do a proof by contradiction. We'll say let X belong to R. We want to show that it is not the case that Sn converges to X. Right? So suppose Sn goes to X as n goes to infinity. Our goal is to get a contradiction. So I'm going to think about this. Now remember, we have -1 and 1, and the only thing we know about X is that X is a real number. So imagine if my X is over here. Now remember, my terms are oscillating in between -1 and 1. Could I think of a way to show that my terms aren't getting close to X? And the answer is yes. What if my X is here in the middle? Well, yeah. What if my X is over here? Yes. Maybe it gets a little tricky if my X is actually equal to 1, or if my X is equal to -1, right? Here's what we need to show. We need to unwrap this. What does it mean to say that it's not the case that Sn goes to X? Okay. So let me add here. So it is not the case that Sn goes to X if and only if it's not the case that for every epsilon greater than 0, there exists an n such that n bigger than n implies the distance is less than epsilon. The distance between Sn and X is less than epsilon. We need the negation of this. Well, that means there exists epsilon greater than 0 such that for all n, this doesn't happen. It's not the case that n bigger than n implies that the distance is less than epsilon. Okay? Well, that means we need to show there exists an epsilon such that for all n and n, there exists a little n bigger than n such that the distance between Sn and x is bigger than or equal to epsilon. So remember, there's a for all here, right? For all n. So when we take the negation, we'll get a there exists, okay? So thinking back to our number line, here's -1, here's 1, and suppose we have s, or x, I think is what we're using. If the x is over here, we need to show there exists an epsilon such that for all of the terms, we can find a term after it that is further away than epsilon, okay? What I'm looking at here tells me I could just use epsilon to be this distance here. So if epsilon is half of my distance to -1, then for any n, my terms, Sn, are all more than epsilon units away. Yes? And the same could be true if my x is over here, or if my x is over here. So in other words, if x is not -1, and if x is not 1, let epsilon be half of the distance from x to whichever one is closer, right? So here's a way to say that. Case 1, x belongs to R, but it's not plus or minus 1. Let epsilon equal 1/2 of the distance between x and whichever is closest. So I want half of the minimum of the distance between x and 1 and the distance between x and -1. Then, for this epsilon, number 1, the epsilon is bigger than 0. Since x is not 1 or -1, this epsilon has to be a positive number, right? Because that's going to be positive, and that's going to be positive. So the minimum will be positive, and half of that will be positive. And number 2, Sn doesn't belong to x minus epsilon, x plus epsilon for all n. So in particular, for all n, there exists an index after that where x is not in that interval. Okay? Now we have case 2. What if x is equal to 1? Okay. So here, suppose x is equal to 1. How can I show that for every epsilon, how can I show that there exists an epsilon? Well, just take epsilon equal to 1. If epsilon is equal to 1, then all I have to do is show that for every n, there exists a term after that index that isn't within epsilon of x. So first, epsilon is greater than 0. And secondly, for every n, either s n or Sn plus 1 is not in the interval 0 to 2. How do I know that? Remember, my terms are just going to oscillate in between -1 and 1, -1 and 1, right? So whatever n is, either that term is -1, so maybe this is Sn, or Sn plus 1 is equal to -1. Either way, you will have a term that is not within epsilon of x. So x can't be the limit, because if x is a limit, then regardless of the epsilon you choose, you're supposed to be able to go far enough out in your sequence to guarantee that all of the remaining terms are within epsilon units of the limit, right? And we notice with this reasoning, there's nothing special about choosing the point 1. This exact same argument can apply when x is equal to -1. So if x is equal to -1, now just consider epsilon equal to 1. Now we're looking at the interval from -2 to 0, right? Epsilon is greater than 0, and for all n, either Sn or Sn plus 1 is not in that interval. So what I'm going to do is modify this to be x minus 1 to x plus 1. Okay? And I'm going to put this to be plus or minus. Yeah? And so now we're done. Let me put a little square. So going back over this, what we're saying is, if your sequence is -1 to the n, to show that it diverges, fix a real number, and we'll show that the sequence does not get arbitrarily close to x. i.e., there will exist an epsilon such that no matter how far you go out in your sequence, you'll be able to find a term that is not within epsilon units of x. Okay? All right, so that's lots of practice with using the definition to prove that a limit exists or doesn't exist. The next thing I want to do is talk about computing, or just kind of remind you of how to compute limits when they're not rational functions, okay? So now we're getting into exponentials and square roots, and things get a little trickier. So for this first one here, we have n to the 1 over n, and I just want to remind you how we handle this. So for this first one here with n to the 1 over n, n is going to plus infinity, 1 over n is going to 0. So this is an indeterminate form, which means we need to rewrite this in a way so that we can tell whether the infinity is growing faster than the 0 is disappearing, okay? So we're going to take our n to the 1 over n and rewrite it as e to the log of n to the 1 over n. Now we can use our log rules, and we'll have e to the 1 over n times log n. So that's e to the log n over n. And then remember that log x over x goes to 0 as x goes to infinity, right? And you can use L'Hopital's rule to verify that. So that's going to go to 0. So this whole thing is going to go to e to the 0, should go to 1. So this limit here is going to be equal to 1. And then we can do something similar here, because if you think about what's happening as n goes to infinity, now that's going to go to 0. So our base is going to be approaching 1, but our exponent is going to be approaching infinity. And we kind of need to figure out who's growing faster. So we'll do the same trick. So you have your 1 plus 1 over n to the power of n. And you simply write it as e to the log of 1 plus 1 over n to the power of n. Bring down the n log 1 plus 1 over n. And at this point, we have like infinity times log of 1. Now remember, log of 1 is going to be 0. So we have infinity over 0, still indeterminate. But if we take the n and write it as 1 over n, now we have a form where we can apply L'Hopital's rule, because that's going to go to 0. This is going to go to 0. So use L'Hopital to figure out, let's see here. So if I had log of 1 plus 1 over x, and then 1 over x, I'm going to do L'Hopital's rule. I need the derivative of the numerator. So that'll be 1 over 1 plus 1 over x times, now I need the derivative of 1 over x, minus x to the minus 2. And then for my denominator, it'll be minus x to the minus 2. Those will cancel out. So, this whole thing is going to go to 1, right? So all of that's going to go to 1, because that's going to go to 0. So all of this goes to 1. So this limit is actually going to be e to the 1. Okay. And then this last one here requires a little bit of a trick. As n goes to infinity, we're looking at infinity minus infinity. Again, this is an indeterminate form. And a way to get around that is to look at the square root of n squared plus 1 minus n. Rewrite it as the square root of n squared plus 1 minus n times square root of n squared plus 1 plus n on the numerator and the denominator. So I'm just multiplying my original term by 1, because I have the same thing in the numerator and the denominator. Okay, and when I do that, I'm going to end up with square root of n squared plus 1 plus n on the denominator. Then the numerator, I will have let's see what I'll have. Well, think of this as a minus b times a plus b. So I actually have a difference of squares in the numerator, right? So that should just be a squared minus b squared. And when I look at a squared, I should get n squared plus 1. So this will be n squared plus 1 minus n squared So I'm just actually going to get 1 over the square root of n squared plus 1 plus n. Now I'm looking at this, and I say as n goes to infinity, this is looking like 1 over 2n. Oh, wait a minute. Oops. This is n squared plus n. So what I have now with the n squared plus 1, this is now going to go to 0. If I go back and switch it to n squared plus n, okay, so now I have n squared plus n minus n squared. So this will now be n, right? Divide everything by n. And I'm going to get 1 over the square root of n squared plus n over n squared plus 1. This is going to approach 1, right? Because that's just 1 plus 1 over n. So I should get 1 over 2. Now, we're not going to use the definition of limit to prove these, right? It makes more sense to prove these limits using limit laws and using properties that we'll learn later. So for instance, once we prove the convergence of power series, we'll say, hey, power series is a function that's continuous. Continuous functions preserve limits. This is the limit of a continuous function. Therefore, the limit of this is going to be equal to e. So we'll do like a reasoning like that to get around actually using the original definition, okay? Now, the last thing I want to do is go over this proof here because it's a nice way to tie together the concepts we've been studying with the completeness axiom and these new concepts about limits. So here's the setup. So Sn is a convergent sequence of real numbers. So Sn is convergent. Okay, we're told that the terms are non-zero and the limit is non-zero. And we're supposed to prove that the infimum of this set here is a positive number. So let's look at this and see, at least get an idea for why it might be true. Now, the setup is we're given a bunch of non-zero terms, and they converge to some limit s, and s is not 0. Now, when I look at this set, which is the set that I'm taking the infimum of, so notice that every element in this set is bigger than 0, right? One of the things we'll prove is that if Sn goes to S, then the absolute value of Sn has to go to the absolute value of S. So we'll prove that. And in my mind, I'm thinking I have all these positive terms here. So 0 has to be a lower bound for this set, right? So S has to be somewhere over here. And I guess what we're trying to prove is that S can be over here, S can be over here, but we don't have S like this. So we're saying that 0 is strictly less than the infimum of the set. That's kind of the idea. It's like if this is our set S, then that right there would be the infimum of S. And we're trying to prove that this infimum is not equal to 0. It's actually bigger than 0. So the first thing we want to do is notice that the infimum actually exists. Why must the infimum exist? Well, remember that's going to be a result of the completeness axiom, or corollary to the completeness axiom. So if you have a non-empty set of real numbers that's bounded above, then its supremum exists and is a real number. Similarly, if you have a non-empty subset in R that is bounded below, its infimum exists and is a real number. So, by the completeness axiom, let's get ready here. Here's a sketch of the proof. So we're going to say, by the completeness axiom, or the corollary to the completeness axiom, and in fact, I might be able to actually cite the corollary. Give me a minute here. Corollary 4.5. The infimum of S exists and it's a real number. So let's let alpha equal the infimum of S. Okay, so remember this is S. Now, we notice that 0 is a lower bound for S because every element in S is bigger than or equal to 0. 0 is a lower bound of S. So, alpha is bigger than or equal to 0. Because alpha is the biggest lower bound of S. Now we just need to prove that alpha is not equal to 0, right? That's the idea. Now, here's how we're going to do it. Remember, we have one key piece of information that we haven't used, and that is that S is convergent. Sn is convergent. So we have our terms Sn, but these terms are getting arbitrarily close to some number, say S, right? So if the terms are getting arbitrarily close to some number, then that means that for some epsilon, we can make it so that all but finitely many of those terms are within epsilon units of S. So you'll have only finitely many terms outside of that interval. So the infimum of this set is actually just going to be the minimum, right? Because you have finitely many of these terms. And remember we said if you have a finite set, then the min and the max exist. So this is going to be our approach. So we're going to say suppose Sn goes to S, right? So, or that's already written here. So Sn goes to S, okay? So that means that the absolute value of S is bigger than 0. Since S is not equal to 0, the absolute value of S is going to be bigger than 0. So say the limit of Sn is equal to S. Then the absolute value of S is strictly bigger than 0. So here's our number line. Here's 0. This has to be the absolute value of S. So let epsilon equal half of that. This epsilon is bigger than 0. So by definition of Sn converging to S, there exists an index n such that n bigger than n implies the distance between Sn and S is less than epsilon. So here's what I'm going to do, because my argument here, the argument that I'm doing is assuming that if Sn goes to S, then absolute value of Sn goes to absolute value of S. So let me put in here, I'm going to erase this, and I'm going to put that here. So this is something we'll prove, or you prove it. This is something you should be able to prove, right? So prove that if Sn goes to S, then the absolute value of Sn goes to the absolute value of S. So then the absolute value of S is bigger than 0, since S is non-zero. So that means this epsilon is guaranteed to be positive. And whenever we have a positive epsilon, that means there exists an index n such that little n bigger than big N implies this distance is less than epsilon. And now I can do my absolute value. So go back to the number line that we have. So remember, here's 0, here's absolute value of S, and my epsilon, right? So this is absolute value of S minus epsilon, absolute value of S plus epsilon. My epsilon is half of the distance between 0 and the absolute value of S. So this point here is like midway, right? Now, Sn plus 1 Sn plus 2, Sn plus 3, da, da, da. All of the rest of these terms, all of these terms belong in this interval, right? So notice that this is the same thing as that location there, and this is the same as that location there, because our definition of epsilon is absolute value of S over 2, okay? So all the rest of these terms are here, so that means that S1 oh, let me put my absolute value in here. Sorry. I should have absolute values here. So absolute value of S1, absolute value of S2, absolute value of S3, all the way up to the absolute value of Sn. This is a finite set. And each of these numbers is positive. Right? So that means that the minimum has to be strictly bigger than 0. Okay? So the infimum of S has to be bigger than or equal to the minimum of this set here and this number here. So all of my terms, remember I have all infinitely many terms, 1, 2, 3. These are the first n terms, and these are the rest of the terms. The rest of the terms are all in this interval right here. And then these first few terms, who knows where they are? Maybe they're over here, maybe they're outside, maybe they're in, some of them are inside and some of them are outside, I don't know. But the point is that whatever's the smallest of them, it has to be something that's positive. And my infimum has to be, a lower bound for the set. So it has to be less than or equal to all of these, right? And I know that the minimum of this set and this number here is less than or equal to all of the elements in S. So the infimum of S has to be, let's see here. So let me step back. So I have a lower bound, and the minimum of these and S over 2 is a lower bound for S. So alpha is bigger than or equal to this min. But now this min is bigger than 0. So alpha is bigger than or equal to this because this min is a lower bound. This min is positive because it has finitely many positive numbers here, and then this number here is also positive. So remember, that's the left endpoint, okay? So we're done. And so let's step back and review what we did. This for a sketch of the proof. So we said, suppose S is this set, and we're trying to prove that the infimum of this set is positive. First, the infimum is a real number by the completeness axiom. Second, instead of looking at Sn converging to S, let's look at the absolute value of Sn converging to the absolute value of S. Now, to get that alpha is bigger than 0, we're going to find a number that's positive that is a lower bound. And the way we're going to do that is we're going to say that we know that the terms of absolute value of Sn, i.e., the elements of this set have to be getting close to absolute value of S, and only finitely many of them are not super close to it. So let's use that to find a lower bound for the set. That lower bound will be positive, and then we'll be guaranteed that our alpha has to be bigger than 0 because it's got to be bigger than or equal to any lower bound, okay? So we said for this limit, just pick epsilon to be half of, right, the midpoint, so that that left endpoint is definitely a positive number. Now, all but finitely many of the terms of your sequence are going to be in here. So that means all but finitely many of the terms of your sequence are going to be bigger than or equal to that left endpoint. And then you have finitely many terms left, but they're all positive because we had this requirement here that each term is non-zero. So the absolute value of each Sn has to be bigger than 0. So you have finitely many over here. And you take the minimum of all of them, and you'll get a positive number. So now you have a lower bound that's positive. So your alpha, bigger than or equal to every lower bound. So your alpha has to be bigger than or equal to this positive number. So alpha has to be positive. Alpha can't be equal to 0. Okay? All right, let me know if you have any questions.